This is kind of cool. It looks like a homemade sub. I've never seen such a thing before. You can take it over to Stone Valley and or Shavers Creek and pop up from the depths. I guess there's emergency surfacing, walrus class. I guess I can see why it's called walrus class. Don't want to do that. See what else we've got. That was that. Stop it. It's kind of fuzzy, I guess. But the same kind of deal, I guess, with a real submarine. I guess a Navy, U.S. Navy, presumably U.S. Navy submarine. Emergency blow. I guess it's emergency egress. Okay, what else? Yeah, I guess that's the only videos we got, Mr. Scott. So I guess we've got 5 minutes, so I won't get going until we are on time. Maybe talk about this. I don't know when this was, 2013. I guess this is in your life experience. The Costa Concordia was a cruise ship in the Mediterranean where the captain wanted to show off by doing a close pass to some people on an island and misjudged it and grounded. And of course it could have been a real disaster because if it capsized, if it wasn't caught by the seabed being close to the island, on the left-hand side where you see it lay, there'd been a huge loss of life. As it was, parts of the boat were flooded, of course, because it was the skin of the boat was breached, but it didn't sink completely, so fatalities were relatively small compared to what they could have been. And then it was a big salvage operation, and so the salvage operation has to refloat it somehow. And so what they did was they built a crib underneath it. They used that crib to attach some buoyancy on one side and then pull it over, cant it over. I guess by using the buoyant tanks filled with water as extra weight to pull it over. Once it was over, attached a buoyant tank to the other side and then evacuated the tanks to be able to float it off and then take it away to salvage. I'm sure it wasn't reused again. And so the topic of today is buoyancy. I hope the BBC don't do a copyright infringement on me to take this down, but they have done it in the past. They must tag these. I guess they can't do it with this per se, but if you use videos sometimes from BBC, they tag them somehow so they know instantly when you upload it onto YouTube. It must be marked in some way to do it. I don't imagine it's kind of AI type things and sorting out exactly what being able to digitally compare what's going on. And so today we're talking about buoyancy after we get done with our discussion about forces acting on curved surfaces. So far last time we worked with planar surfaces, forces acting on a plane to get resultants. So we'll take that and maybe look at curved surfaces. Of course, many curved surfaces we could approximate as multiple planar surfaces, and we will do that in some way. And so that's what we will do later on. And I guess the other things that I have on here, we showed the video of the emergency breaching. If you have an emergency breaching underneath a boat, it's not very happy for the boat. And of course that was what happened, not in this case, but I think to the Ahimi Maru, which was a Japanese training boat for young guys, many guys I would imagine, but young people learning to be fishermen, trawler captains or trawler hands, came up underneath it off Hawaii and unfortunately sank the boat, and with the resulting unfortunate loss of life. And the other thing that I guess the Kursk, I guess I got rid of the Kursk, but I guess not related So there have been many submarine disasters where obviously you use buoyancy to rise. You have compressed gas and you pump that gas into your tanks, which are full of water. Water gets expelled and you rise by buoyancy. There was a submarine lost in the middle of the Pacific, and so the desire was for the CIA to recover the code books from the submarine. So they put up this ruse by which Howard Hughes would build the Glomar Challenger, a boat to go around the world looking for manganese, to mine manganese nodules from the plate boundaries in the deepest parts of the ocean. And actually this boat was not a mining boat at all. There's a whole narrative in the press of mining on the seabed, but it was actually a boat with an open bottom that could go down and was looking for this submarine, and ultimately recovered the submarine by raising it into the hold inside clandestinely, I guess, which I think is a kind of an interesting story if you know that. Howard Hughes, of course, is the guy who made his fortune on the tricone bit, the drill bit, which is used, for every drilling project around the world. So today we're going to talk about buoyancy, but as we have in the past, we'll kind of recap what's going on. I guess homework 2 is closed. I need to write the test for for week 5, not next week, but the week after. Once I've done that, I can make a review session. That'll be posted no later than Thursday, but it may be posted sooner than Thursday. So you can look at the ones from previous years to see what they are and correlate them with the tests, just to prove to yourself that I'm not spinning you a yarn when I say what the 3 questions will be, and allowing you to perhaps concentrate on them. So that will go up sometime. In week 3, we said that we'd put you in groups for the presentations. I think that hasn't happened yet, but will happen quite soon. Week 3 is only an arbitrary date because it's after the drop ad deadline, so we're pretty sure that the groups are going to stay as groups without people leaving the course or joining the course, which is just a bit of a pain to have to deal with. So that's that. Anything else? Yeah, no, that's about all the announcements I have, I think. So let's get with this. All right, so in terms of, I don't know what that is, your device battery is low. That's my pad, so hopefully it'll keep. Okay, so recap. We were talking last time about forces on structures. Pardon me. You know that this relationship is true always. The resultant force is equal to unit weight times the depth below the surface. This term here is the average pressure, and multiplying it by the area gives it the force. We can resolve forces horizontally and vertically into a resultant if we have them, just by noting Pythagoras. And we could also determine the angles for this if we wanted to, just by trigonometry. And we can also get the location of where the force acts, y sub r, from this parallel axes theorem. And just it is an important relation, so let's kind of draw it out again. If we have the x and the y axis, if you have the water taking on the location of the x axis, and if you have a structure that looks like this, then we can rationalize all the components in the centroid of my pad, as I hold it up on my tip of my finger, is below the surface by some amount h sub c. That is this term here. And that the location where the resultant force acts, F sub r, is always perpendicular to this plate, and it's always at a location that's given by 2 components. The first is the slope distance in the plane of the plate YC, which is the distance from the surface to the centroid, where the balance point is on the plate, and an amount below there which is, we called last time delta YC. And so in this term here, the first term is YC. Sorry, not is it? The second term is YC, and the first term is delta YC. So we have that. You can also do it, we didn't talk about it, it's not so useful. You can also do it to find, we've assumed from the geometry that it's in the center line directly below the centroid. So the portion where it acts is below the centroid, it has to be because it's sloped. Where is it within that line? Well, just by symmetry, it has to be bang in the middle. You can also show that by proving it, well, by demonstrating it with this, I don't know what color I'll use. By using this equation is exactly the same. This is XR is equal to X sub C, that might be a bit light, plus delta XC. And so this would be the fact, it's not very easy to do here. This would be X sub C. This amount here would be delta XC. But in this particular case, delta XC is 0. And you could show that just by using this. So you have to use a slightly different value for the second moment of area. Those are given in the in your book or in this. They happen to be this term here. And so that second moment of area ends up being 0, which means that delta X has to be 0 for this particular geometry. And so those are the things that we used last time to look at this. I don't have, I'm not going to leave this, but another useful thing to do, I didn't need to do that. Another useful thing to do is, if I can find it, I think it's this one. Yeah, okay. So I've used the expression before, there's more than one way to skin a cat. If you want to skin a cat, I don't know who does. But we did this example last time, and it's perhaps useful to look at this. I'm not going to leave it on long enough. Well, you could try writing it down, but it's pretty complicated. I actually did this live, I think, a few years ago. But the idea here is that, let me get back to this. This left-hand diagram was exactly the form of the way we did it last time. We looked at the pressure distribution on this vertical wall. We looked at the pressure distribution on the base, and we could calculate where the location of that was and the magnitude of FH was, and the location and the magnitude of FV. And we were really drawing, if you like, a control volume by this line around the hinged gate. If we didn't want to do that, we could do it a different way. Of course, these all have to give the same results. So the other way could be that we could draw a control volume, which would be this box here, in which case we'd have to look at all the forces on this external box. So those forces would be the pressure acting on the left-hand side of the box, the pressure acting on the upper boundary of this water, and you have to add the weight of the water to this. So in this case, FH is exactly the same as FH here, but the vertical force is now the sum of the vertical aggregate pressure multiplied by the area on the top of the water, due to this height of water, and the weight of the water that's underneath it. So in other words, the vertical force will be the sum of these, V1 will be the sum of the weight and the pressure. And so another way to do it would be to draw the control box, instead of being around here, to draw the control box all the way up to the surface. And if you do that, you remember that the water was up here, so you have this distribution of pressure on the left-hand side, but you also have a distribution of pressure on the right-hand side here, which has to directly cancel this. So FH, if you take off this little part here because it cancels with this, will be equal to FH here, so that doesn't change. But now the weight acting downwards is not going to be any pressure here because we don't have a control volume there, but it's going to be the full weight of fluid acting downwards. So FV1 will just be the total weight equal to this. And of course that weight here is exactly the same as this distribution of red at the bottom. And so I don't want to confuse you, but I just want to make the point that there are more than one way to do this, and so every way would give you exactly the same result in this particular case. And so this is kind of useful because this example guides us in to be able to talk about how to do forces on curved surfaces, which is kind of the next thing we'll talk about, and then buoyancy after that. So anyway, so this is one way to do it. So this will be certainly recorded, and so if you want to be able to torture yourself with that, you can go back to that. Okay. All right, so the diagram you saw on the bottom there was exactly the same as this. We know where it acts through the center of pressure. So what we'll do today is we'll talk about some forces on curved surfaces, but we'll also finish by talking about buoyancy. And of course, you know from Archimedes' principle, probably, that the buoyant force is equal to the unit weight of the fluid displaced. So it's the unit weight of fluid by the volume of fluid that's displaced. And so we will use that in our future. So just to be able to perhaps reinforce some of these ideas, go through a couple of quick examples just to see how these things are used. This is kind of a contrived example because why would we ever cut the water in half? So it's not a practical example in that way. But if we chose to, we could cut this culvert in half that's half filled with water, and we could look at the magnitudes of the forces that are acting on this. It's instructive in some regards because it says something about the punchline, I suppose, is that since all individual pressures act normal to this boundary, and the normal to this boundary all go through this point, then the resultant force actually has to go through this point as well. We can show that. I'm not sure we need to, but we could do. So how would you calculate the forces acting on this? If you cut it in half, there has to be a force acting horizontally, has to be resisted by another force outside it, acting in the opposite direction. If we want to calculate the force that's acting horizontally, we can calculate just from doing what we did before. We can draw this with our little line. So it's probably going to get a bit busy. But this magnitude, if you can see it, that's not supposed to be at an angle. This is the depth of the centroid, y sub c. It's going to be 1.5 feet. It's not going to be where the point of action is. That will be lower than that. But the force that's acting is going to be equal to the unit weight of the fluid times h sub c times the area of which it acts. The area, I think in this case, is going to be 3 times 1 foot into the page. So this is going to be the expression. Unit weight of water. The depth of the centroid is 1.5 feet, and it goes 3 feet into the section. It would be times 1, right? That'd be the other way to 3 feet is 3 times 1 feet, because it's 1 feet in the section. And you can calculate what F1 is, and it would be equal to the reaction to it. We can do the same for FV. The pressure acting on the top here is 0. So it's just going to be the unit weight of the fluid. And so the weight is going to be pi r squared over 4. So this is the volume, pi r squared over 4. I guess it'd be times 1 foot, times the unit weight, and that comes out to be equal to this. And so FV has to be the opposite of that. These have to balance. So we have both F1 and FV. If we wanted to, we could take these two magnitudes, one of which is F1 and one of which is W. And we could look at the resultant of those if we wanted to, just by taking the squares of these. The horizontal force and the vertical force squared, square root, gives us the resultant. So the magnitudes of the forces are 441 and 281 pounds. And the resultant is bigger than both of them individually, as you'd expect, right? Just from the length of the vectors. And what we could do, alternately, we could also define from the angles, the magnitudes or the angle at which it works just by looking at the trigonometry of it. So I won't do that. But I will make the point that if you then looked at this, and so we have, if I can't draw this very well, maybe I do it in red. If we have the force FH acting horizontally, and we have the force W acting vertically, we could write an expression, and we know what these lengths are. This length here, let's call it length horizontal, because it acts on this, and this would be length on the weight. We could take moments around this central point, and you see that they would be in opposite directions, so we could do one, it would be LH multiplied by FH minus LW times W, I guess, equals, let me do it differently, some other force, which this would be the resultant, equals FR times the, I haven't drawn this very well, by some length between the point A and the location of this force. And so this would be equal to force R times L resultant. And if you go through this, we know what this length is, we know what this force is, we know what this length is, we know what this force is, we know what this resultant is. You can solve for LR. What you'll find out is that LR, by definition, is equal to 0, because it has to act through this point here. And the most obvious way of stating that is that every single resultant from the pressure on this boundary has to pass through this center, and so in aggregate, the net force also has to pass through the center. The resultant passes through the center. Perhaps it's not an important observation, but it's kind of, actually it is an interesting observation, merely from the case of this. And so this is called a Tainter Gate. This is a picture I took many years ago in Nova Scotia. And it is the way of having a gate which holds water back, which kind of has the minimum weight to it, minimum strength. And the minimum strength, because this surface is curved, so that when you drop it into the water to cut off the flow, then because every single pressure point acts normal to the surface, these all act through this fulcrum. So there's no net moment of this, and it ends up being a very light gate to be able to deploy. And so that just acts on the idea that because all the fluid pressures are normal to this surface, the normal to this surface, all those lines pass through this fulcrum, you can make a gate that has no net moment on it, and therefore it doesn't have to be particularly strong to be able to resist the forces behind it. Yes?
Okay. If the net forces are acting in that direction, can you just reverse it and work this as well?
Say it again?
If the net forces are acting towards the point,
You could have something upstream of it rather than downstream?
I'm
Yes.
like from right through.
Yes, upstream to downstream.
You
Yes.
also have it, other way around.
Yes. Yes. Because they'd all act through the fulcrum, right? But it's usually used with the upstream head on the down. This would be a higher head up here and a lower head down here. But it would work the other way as well. We can do the same thing with fluids behind at depth within a system. Same kind of analysis as before. We would have to be able to split this up in some reasonable way to calculate what the resultants are here. If you look at those magnitudes on this segment, what would they be? The forces acting horizontally, what would the forces be? How would you calculate it? Well, the easiest way to calculate it would be to calculate it. This is unfortunately called H sub C. We don't want to call it H sub C. It's called H sub C because it goes through C, but that's a confusion. So this would be the real H sub C, which would be this length here divided exactly in halves. And of course, the midpoint of this would be equal to whatever this height was, with this portion HA added onto it. And so we'd be able to calculate what the forces are here. So it would just be that F2 is equal to HC unit weight, which of course is the average pressure multiplied by the area of this gate. If we wanted to calculate what the force was here, then what's it going to be? This is now going to be, I guess, since this is force F1, let's call this HC1, let's call this HC2. So F1 would be equal to HC1 times the unit weight of water times area 1. And area 1, of course, would be this length here multiplied by the length into the page. But we have, in addition to the force acting here, so in other words, this would be a uniform distribution of forces acting here. This would be a pressure acting here, which is exactly the same as this amount, right? But then going down here. And so the resultant F2 is due to this trapezoidal distribution, and that would exactly come out from this equation here. This is a uniform distribution, which comes from this, and we have to use the weight of the fluid on top of this, which is going to be the weight is equal to the volume multiplied by the unit weight. And so that's just a force per se. And so we can calculate what those are and go through it. So it's just a matter of dissecting things in an appropriate way. And it's just like the example that we looked at before, in that the example we looked at before was this. We describe it in a different way. In this particular case, we're actually doing this, right? So that instead of being straight, it's curved surface. It has a weight inside it, has a force acting horizontally, a force acting vertically. And if we wanted to, since we know the force is acting on this gate, the idea is that if it's hinged here, we could calculate what force we have to apply to keep it closed. Because clearly we can take moments around this due to this force acting downwards through this lever arm and this force acting horizontally through this lever arm. So that's kind of our desired approach to do that. So do we have some examples? We don't need to go through that. That's too complicated. Just perhaps some examples just to get you thinking in the right direction. Because it really is just being able to think about what the problem is and trying to dissect exactly what it is that you're being asked to do. And so this is an example where there's a cylinder that's sitting on top of the water, has some weight to it. It's sitting in oil, I guess, rather than water. It's abutting against this. And so if you think about it, you could draw a free body diagram around here that includes water, or oil rather, in the corners. You know that the distribution of forces on one side is going to be here. And the question is asking you what force is being applied at A as this gets pushed into it. And so you have to think about it a little bit. It's a bit tricky. I guess you have to assume that there's no flow being allowed out of here. Because you know from what we've talked about before that the pressure at this point here has to be the same as this point here, and this point here, and this point here, and here, right? Because they're all in the same straight line, horizontal line. So the pressure at this point here, this length here, has to be exactly the same as this length here. And we know that as you go up within a fluid, the pressure rises according to the unit weight. So this gradient, it can't really go up to this point to be zero pressure, because as you go up, we know that the unit weight is equal to dP dz. So we know that if we look at the pressure distribution with depth, it's minus, right? That it always goes up at this rate. And so, in other words, this is given by, this is unit weight, and this is 1. Just from rewriting it as this. This is pressure, unit weight, so these are the same, and this has to be 1. And so this has to rise at exactly the same gradient as this. And so the pressure at this point here actually has to be the same pressure, I'm not drawing very well, has to be exactly the same pressure that's acting at this point here. And so this trapezoid would be looking like this. And so if you want to calculate exactly what those forces are, then you'd have two forces. You'd have F left is equal to this amount here, and F right is equal to this distribution here, and you can just write them as equivalent to each other, that FL has to be equal FR plus FA. You don't know what FA is, but you know what each of these are because you can calculate what this distribution is. So I guess if you wanted to calculate this is the same as having so FR would be equal to this. What would it be equal to? Well, the depth of the centroid is at this point here, so it's 3 feet plus 1.5 feet, so it'd be 4.5 feet, which is H sub C, times the unit weight of oil, times the area, which would be 3 feet times 9 feet. I hate English units, but that's the deal, 9 feet long. Okay, makes sense. So you just have to know what the question's asking you. It's all worked out and in your notes below so you can see it, but the rationale is that as you go horizontally, the pressure here has to be the same as this pressure here. It has to rise up at the same gradient because this is fundamental requirement. And so the pressure at this point A has to be exactly the same. I guess you could do this, right? You can traverse from point A all the way to this point here. Whoops, well, that's quite nice. All on the same level. And so the pressure at A and this point here have to be the same. And so this length here has to be the same as this length here. If you can see my stuff. Hopefully you can see my stuff. If you don't see it, so. Okay? So you can go through that. Too complicated. This is again showing that you can skin a cat multiple different ways. I'm not going to go through that, but we'll talk about. So, okay. So those are pressures on structures. Of course, pressures on plates and structures have ramifications for buoyancy. It's really exactly the same behavior. And the easiest way to show that is just by looking at trying to derive Archimedes' law. And the easiest way to do that is to show exactly this. If I draw a line here for pressure, and pressure versus depth, it's negative z, I guess, right? Because we're going downwards. Positive z is upwards. And I guess this is the water surface here. So if I continue this here, so if I draw pressure with depth, then this is the P is equal to Z unit weight. Z is negative, but you know that already, so allow me that. And so what you're looking at is that there's a pressure that's acting at this top part, which is given by this. And there's pressure that's acting at this bottom part, which is given by this amount here. If you look at the difference between those, so I guess we could call this P1, we could call this P1, and we could call this P2 as the sum of these two. Actually, I didn't. Let's not do that. Let's call this P1, but let's call this whole thing P2. Then we can calculate the forces as being equal to the area of which this is applied, which is dA. multiplied by the difference between P2 and P1. That's the net pressure that's applied, which is this term here. And we can rewrite this magnitude as the unit weight multiplied by this height. So this is just this height of the column. And so immediately what comes out of this is that the incremental force due to buoyancy is equal to the unit weight times the volume of the fluid displaced. So this term here, the height times dA, is just this differential column. And if you integrate it over the whole system, it's the volume of your system. So it's a long way of saying that basically, as what you know, is that Archimedes' principle says that the buoyant force that's applied to any body that's submerged is equal to the volume of fluid that is displaced by that body multiplied by the unit weight of the fluid that's displaced. Very straightforward. And so well, we can do that in lots of different ways, more complicated ways, but that's the basic tenet that we want to understand. And so in anything that we want to understand in terms of how buoyancy acts, we can resolve forces once again. We have to resolve them in a specific way so that they make sense. And so here's an example that's in your notes also. We have a spherical buoy, I call it a buoy. It's a diameter of 1.5 meters, so it's back in SI units again. It weighs 8.50 kilonewtons. It's anchored to the seabed with a cable. It's underwater completely, which is useful, makes the problem much easier. What's the tension in the cable? It's pretty straightforward. So the idea is that you can just take a free body diagram. Not sure how well, it's not a bad circle. And you can look at the forces that are applied onto it. The forces are the weight which is applied. The force is the buoyant force, which is equal to the unit weight times the volume displaced. And attached to this is a cable which has a tension in it. And so you can just resolve forces. If you resolve forces, you get this expression here. I can write it out. You get T plus W is equal to buoyant force. In this particular case, you're given the weight of the buoy. You know, the weight presumably has to include the weight of air which is in it, which is trivial, but is included in it. And if we know that this magnitude here is equal to the unit weight times the volume, I guess the volume is equal to 4 over 3 pi r squared, cubed rather. Dimensions, right, it has to be cubed since it's a volume. The weight we have already in kilonewtons, not in kilograms, so it's already a weight. And if we substitute for these, then if we know this, we can solve for what this value of the tension is. And I'm sure you can do the working to figure that out. So it's pretty straightforward. So same idea, I guess, we've kind of talked about it in terms of balloons. You know, that's kind of a does balloon have 2 L's in it? I think so, right? Can't remember. Anyway, it doesn't matter. So we know how a balloon works. We've said that simplistically, a balloon, the density of the gas in the balloon has to be less than the density of air around it. And so this is borne out by the fact that the net force acting upwards, the buoyant force, is equal to the displaced volume multiplied by the density of air minus the density of the gas. The gas isn't zero density, it's just the density of the gas has to be less, so this has to be a positive value and multiplied by acceleration due to gravity. So in this particular case, this is the expression that would give the force that is applied. And so if you wanted to apply a tether to it, like the guy that we looked at sitting in his deck chair, floating above from his garage with 20 balloons attached to him and a rifle to be able to shoot them out one by one, this is the expression that would say what the magnitude of the tether force should be. And so this is useful to us because we know that the density of air we can get from the ideal gas law. I think we've said this before. So we can rearrange that in terms of density, and that is equal to pressure divided by RT. And so in other words, if we want this density of the gas inside the balloon to be less than that of air, we can do a number of things. So we want this density to decrease. So to do that, we can either increase the pressure or we can decrease either one or both terms on the bottom. So if you want a balloon to go up, you can either, what am I doing? No one said anything? Come on. You can either decrease the pressure. Balloons are flimsy, so if you decrease the pressure, the volume of the balloon will just change, unless it was rigid, and you can't make a rigid enough balloon that's light enough to be a balloon, and so that's not really a viable option. But you could either increase the gas constant, and that means that you put helium in it instead of air, or you could increase temperature. You could make it a hot air balloon, and in which case the pressure inside the balloon will be the same, but because the temperature is higher, the density of the fluid will change, because as you heat it up, it will expand slightly and displace more volume. And so those are the mechanisms by which you can make a balloon go up. This was the question here very specifically says that the buoy is below the surface. And that's important because the magnitude of the volume displaced, if this intersects the surface, of course, like a ship, only half of the balloon, or the buoy, is in the water. And so the volume displaced is only the volume of water that sits below the water line within the buoy. And so things get a bit more complicated, but I guess get a bit more interesting if you allow it to sit on the surface. If it's submerged, I guess the other thing we should know is that in the same way that we talked about the centroid of this plate being in the middle, but the center of pressure being some location where the force acts, which is below the middle point of this plate, that's also true for the systems where you have the buoyant force. The buoyant force acts through the centroid of the displaced volume. So the buoyant force would act through the balance point of this, if this was the geometry that you see here. So the buoyant force acts through the middle of this shape, which would be the centroid of the shape. And if, for instance, it was a yacht and had lead in the keel, the center of gravity of this structure would be lower than it. And so the idea of having the center of buoyancy above the center of gravity is that if you tilt it one way, the moment that this applies is always to right the boat. So that's why a keel works on a boat. You have a very low center of gravity. It's below the center of buoyancy, where the buoyant force acts, and therefore it always rights the boat. If you reverse that, then you have the opposite. If you have the keel in the top of your submarine, then the center of buoyancy is again in the center of this shape. Then if you move it off by tilting it slightly, then the moment is active by moving this downwards and this upwards, and so it'll just self-right. And so if you throw a cork into water with a tack on the bottom, the cork will always float with the tack in the bottom. It's a bit different from this because the cork will float outside the water, right? Because it's freeboards. So it's relatively straightforward. What happens in submerged bodies is that you have the center of gravity below the buoyant force, where the buoyant force acts because it self-rights itself. Good for a lifeboat. Lifeboats are self-righting. It's not very complicated in this case because everything's below the water. And of course, I guess if it's a lifeboat, you don't want to be below the water. It gets more complicated if you're floating on the surface. Same principles apply. The center of gravity always acts wherever it acts, based on, it would be the balance point, including, so in other words, if it was a yacht and you put a hole through this and tried to suspend it, it would be where the hole was that you could put it, that it would stay in exactly this position without rolling over. So that would be the balance point. But if you submerge it partly below the water, then the center of buoyancy is controlled by the area, only the area which is below water, right? So the buoyant force is the centroid of this green space here, which I didn't draw very well, but you get the idea. And so the buoyant force is given by this outline here. It's the centroid of this area here, the buoyant force. But the center of gravity can be anywhere. And so if you have the center of gravity above it, then in this particular case, this would be a point where if the center of gravity is above it, it would restore, because the net moment here is to push this buoyant force up, push the center of gravity down, and so the net restoring moment is to right it. So you have to choose exactly where you'd want to put your components to be able to do that. If you have your center of gravity really high, then the other manifestation of this is, again, the zone which has the buoyant force is acting in the centroid of this displaced volume. If you tilt over, it'll change slightly, but not very much. But in this particular case, the center of gravity and the buoyant force, if you tilt it over, you can certainly see that the moment that you give is acting downwards here and upwards here, and it'll go exactly upside down. And so it becomes a bit more complicated when you have a free surface involved, because you have to think, because the location of the center of buoyancy is changing as the shape of the submerged portion changes, because it changes the volume of fluid that's displaced. Well, I've got 10 minutes, 5 minutes. Let's do this. Okay, what's the point of this question? It's quite a clever question in some respects. The idea is that you have a tank. It has a plate on the top of this tank, and you're applying a pressure inside here to act on this plate. This plate is held down by a block of something, a brick, that's in water and is on a tether. And the question is, basically, what is the pressure that you have to get to for this plate to move up? And so it's only complicated by the fact that then the pressure is defined in terms of a manometer, but we'll ignore that for now. So what do? We can draw a free body diagram, which is this one below. The plate has an area on which a pressure acts. It's air, and so I guess the code for that is it's a gas, and so the pressure within a gas is going to be the same here as it is here, right? Because of the unit weight is so small. That's not going to be true for the liquid, and so I guess I could draw that here. So if the liquid is here, like this, then the pressure distribution, if I draw the pressure diagram, if this is pressure, then the pressure in the gas is going to be equal to some amount. Oh, it's gone crazy on me. The pressure in the gas is going to vary not at all with depth, but once it hits this, it's going to vary with depth. So this is going to be what we said before. This is unit weight, right? And this is 1. This is unit weight of the water. And so the question is, in resolving the forces, the pressure is going to be this pressure here, multiplied by area. We know the area, but we don't know the pressure. We know the weight of the block, because you're told what it is in terms of its volume and its unit weight. And we're also going to have a buoyant force acting up and the buoyant force will be equal to the unit weight of water multiplied by the volume of the block. And the reason that, and you probably already realize this, is that if the pressure was 0, then the pressure in the water, in the gas, would be this, and the pressure in the water would be this. This curve and this curve are parallel to each other. And so the point of buoyancy is that if you look along here, the difference between the pressures at the top and bottom of the brick, the difference in pressure here, I'm holding the wrong part of the pen, it's not liking it very much. So the point is that this, the base here is this. So this triangle here and this triangle here are exactly the same. The point is that by applying a pressure on the top of here, we don't change anything to the buoyancy. It's still the buoyant effect. This buoyant force is still the buoyant force, and the reason it doesn't change with the pressure that's acting on the surface is because it only cares about the difference between the pressures at the top and the bottom of the brick. And that difference, the absolute pressures change from when it's pressurized to when it's not, when it's pressurized to when it's not pressurized, but the difference between these two pressures doesn't change at all. And so the free body diagram is just this, that the weight has to be equal to FB plus pressure times area. And if we solve this expression, we know what the weight of the brick is, we know what the buoyant force is because it's equal to, did we write it somewhere? Wrote it here. We know what the area of the plate is. We know that the pressure doesn't change. The plate, I guess, could be inclined. It would still be basically the same pressure because it's in a gas. This is the distribution. And the only thing we need to figure out is the pressure. Once we know that pressure, that's a magnitude, then we can go and use the manometer equations to be able to figure out that if the pressure that blows the top off is this pressure and this pressure and this pressure, they're all the same because they're these magnitudes here, then that's also the same pressure as is acting here, and we can use the manometer equation to be able to tell us exactly what this would be. Right? So in other words, we could use pressure air plus minus, right? Minus unit weight of mercury times H mercury equals 0. Atmospheric here, by definition, I guess I could also write this as PB. So you can solve absolutely for what this pressure is. We'll call it pressure sub A. And so we know what this is. We know what the unit weight of mercury is. We know the atmospheric pressure has to be 0. And so the only thing we have to do is calculate this height of mercury. And if we know this height of mercury, we know from trigonometry that this is H, and this is H sine 30 degrees. And so we can solve, sorry, that's not right. This is H, and so this would be delta H. So delta H sine 30 equals H. We know what H is, we know sine 30 degrees, and so the only thing we don't know is this. And so it's worked through here. And so I guess the only tricky thing to think here is to realize that buoyancy doesn't care about the pressure that's acting on this surface. It's exactly the same. And the reason it doesn't care is because of this idea that it's the difference between the pressures on the top and bottom. You can think of it that if you're taking the volume of water out of this that's equal to the volume of this thing, then you're just removing the reason for the pressure here being different from the pressure there. The whole reason the pressures are different in those two locations is because of this mass of water that's in there. If you move the mass out of it by displacing it, then the buoyant force is what results. If this has some weight to it, you have to include this weight in it as well. So you have to be interested in not only the buoyant force from the volume of fluid that's displaced, but also the weight of the thing. If it's a lead brick, for instance, has some weight to it. And that's about it. That's all I was going to do. So in terms of this part of the class, fluid statics is these first 3 weeks plus Monday. Monday we'll talk about accelerating fluids. In other words, where you have a beaker and you accelerate it across the room, like the tank cars we talked about, having the flared sides, and the elevation of the fluid in the bus window, the double glazed window, as it accelerated. We'll talk about that on Monday, and that'll be the end of the first part.